Welcome to this short video exploring some of the ideas in higher mathematics, looking at trigonometry and the addition formulae. And we'll look through some example questions to explore some of the ideas and hopefully help you understand the concepts a little bit more. So there are 5 useful expansion formulae which you will need to be able to apply correctly. You do not need to memorize these, they will be provided for you in the formulae sheet. The first 2 are very straightforward. It's how to expand sign of a sum, a plus b, or a difference, a minus b. And we find that sine of a plus b is just sine a cos b plus cos a sine b, and if it's minus, then also we just have the minus sign. So sine, cos, cos, sine. For the cos expansion of a plus b, we have cos a cos b, so the cos terms stay together if you like, but if it's plus, we change to minus in the expansion, and then sine a sine b. And equally, if we start with cos of a minus b, then we can have an answer that will have cos a cos b plus sine a sine b. So notice that change of sign in the cos expansion. That's very important. Now we use those for simple exact values. If I want to find the cosine of 105 degrees, I could write that as cos of 60 plus 45. And we know that cos of 60 and cos of 45 are both exact values that we can determine with the use of exact value triangles. So it's quite often the kind of question that we might see in an exam. Now from those we can derive these 3 expressions. First of all, if we change b for a, then we'll actually have sine of a plus a, which is just sine of 2a, and that expansion becomes 2 lots of sine a cos a. Effectively, these 2 are just the same, and there's 2 of them, so it'll be 2 sine a cos a. Now again, you don't need to know how that is derived, you just need to be able to use this correctly. And for cos 2a, if we do the same thing, we end up with cos squared a minus sine squared a, which if we play around with this and use the fact that sine squared a plus cos squared a equals 1, we can actually derive 2 other forms for this expansion. Now, you can look into this, you can study it, but ultimately we need to be able to use these correctly. Let's look at an example of how we might apply that in an exam question. So here, very common, we might be given 2 triangles or a diagram that involves more than one triangle. We're directed towards 2 angles, angle A and angle B, and we're given a number of lengths. And our task is to show that the exact value of sine of A plus B is just 2 over root 5. Now we do that by drawing these triangles separately, very clearly, by using Pythagoras' theorem to find the third side. In this case, it's the hypotenuse that's missing in both triangles. And then we can write down some trigonometric ratios. We know that sine of A is opposite over hypotenuse, or 1 over root 2, and cos of A will also be 1 over root 2. Remember, you can pause this video at any point if I'm going too fast or you want to think carefully about some of the ideas. For the other triangle with angle B, we can also work out sine of B and cos of B carefully, and then we use the expansion. Sine of A plus B is sine A cos B plus cos A sine B. These will now be carefully substituted so that we don't make any mistakes, and we multiply top by top and bottom by bottom so that we have 3 over root 2 root 10, but root 2 root 10 is actually just 2 root 5 because root 10 is root 2 root 5. So the root 2 times the root 2 will give me 2, and there'll be a root 5 left. Anyway, you can study what I've done here, but we're just finding the final value of 4 over 2 root 5, which is just 2 over root 5, as required. There are many of these kind of questions. They're usually fairly straightforward. The ones involving subtraction can be a little bit more difficult. You may need to find one of those, but I'm sure that you'll be able to practice those and become more successful. Moving on then to example 2, and here we have a situation where we're told something without a diagram. So we're told that cos of A is root 2 over 5, and we're asked to find the exact value of cos of 2A. So we're only given the single angle, and we're asked to find a value for the double angle. So this is now the double angle formulae. So we know that cos of A is root 2 over 5. We should immediately sketch a triangle. And if we label this angle A, we know that the adjacent is root 2 and the hypotenuse is 5. With the use of Pythagoras' theorem, we can find that this is root 23. That'll just be 25 minus 2. And we can then say that sine of a will be root 23 over 5. Now, to find the cos of 2a, we need to turn our attention back to those expansion formulae. And in these situations, it's usually a good idea to choose just the first expansion, although any of the three choices will work. So I'm going to use cos 2a equals cos squared a minus sine squared a, because I have cos of a and I have sine of a. So it'll just be cos of a squared minus sine of a squared, which is 2 25ths minus 23 25ths, which in this case is minus 21 25ths. So we actually have a value for the double angle using the single angle values. And that would be the end of that question. That's an unusual example, but certainly explores some of the ideas. Now, the primary purpose of addition formulae and double angle formulae is to help us to solve trigonometric equations. So example 3 is now to look at a trig equation and how we might use these formulae to solve successfully. Solve the equation sine 2x equals 6 cos x, and we want values for x between the range 0 and 360 degrees, inclusive. So what we can do here is we can write down sine 2x minus 6 cos x equals 0, simply removing 6 cos x from both sides. We always want to have a 0 on the right hand side. And here we need to use the expansion. We cannot solve an equation normally that has a single angle and a double angle, so we have to remove this and replace it with the single angle expansion. So remember that sine 2x is just 2 sine x cos x, so that's what we replace it with. Now this expression has a common factor. The common factor is cos x, so we remove that. 2 cos x. So 2 cos x bracket sine x minus 3 equals 0. And we now have to solve two equations. Two of these expressions could be 0. 2 cos x equals 0 leads to cos x equals 0. And this one leads to sine x equals 3. Cos x equals 0 we can solve by sketching the graph or by understanding that that is just the points where it crosses the x-axis. That will be x equals 90 and x equals 270. And sine x equals 3 is not an equation that we can solve because the sine graph has a maximum at 1 and a minimum at minus 1, so it's not possible for sine x to equal 3. So we just say that there's no solution, or we just make some comment that we can't solve that. It's important that we do that. It's important that we make it clear to the examiner that we understand that there's no solution to sine x equals 3. If you just leave it blank, then they may think that you didn't know what to do and you weren't aware that it wasn't actually solvable. So our final answer then is that x equals 90 and 270, and that would be the end of this question. In example number 4, I want to look at a more difficult trig equation. This time we have 9 sine x plus 4 equals 2 cos 2x, and again we want to look at the range 0 to 360. So far we're working wholly in degrees, but we may have to complicate things by looking at a radians example. So we have 9 sine x plus 4 minus 2 cos 2x equals 0. This time we're substituting the cos 2x, and we have to make a decision of which of these three expansions we should use. And what we'll say here is that in the previous example, there was only one choice. Here we need to have a strategy, and the strategy is very simple. If the equation already has a sine term, then we will choose the expansion involving sine squared x only, so that we eradicate any mention of cos, and we're working only in sine. If there was a cos term, we would choose the one involving cos squared x only, and in these trig equations we never choose this first choice, cos squared x minus sine squared x. You'll remember I used this one earlier in a simple addition formulae triangle question, but in the equation we use this one or this one. So cos 2x is replaced with 1 minus 2 sine squared x. We now need to break the bracket here because we had 2 lots of this, so we now have 2 lots of this term. So it'll be 9 sine x plus 4 minus 2 plus 4 sine squared x. This equation should be rearranged so that sine squared x terms are at the beginning. So 4 sine squared x plus 9x plus 2 equals 0. And then this will be in a normal question, an expression that can be factorized. Very, very rare that you can't factorize it. Very rare that we would have to use a quadratic formula. Now, to help with the factorization, it might be a good idea to just write this down in a simpler way. If sine x was just x, then this would just be x squared. So it's actually just this quadratic here, 4x squared plus 9x plus 2 equals 0. That's still difficult to factorize. You've got to think very carefully, but we eventually will come to the right factorisation. 4x and x, 1 and 2. If we break that bracket, we have the quadratic here. So taking this idea and putting it into the trigonometric quadratic, we have 4 sine x plus 1 and sine x plus 2 equals 0. As before, we solve each of these trig equations now. Sine x must equal minus a quarter, or sine x equals minus 2. Very quickly, this one has no solutions. Here we will need to use a calculator, and we need to identify which quadrants our answers will lie in. Sine giving a negative value will only occur in quadrant 3 and 4. So we know that we have to find 180 plus the key angle and 360 minus the key angle. The inverse sine of 1/4 is 14.5 degrees. So we need 180 plus that value and 360 minus that value. And these are the two answers to this particular problem. We can only solve this trig equation by making that substitution for cos 2x. It's important that you practice that skill and that you are very clear about how to solve these trig equations. Example number 5 is very similar, but this time we'll work in radians. Solve 2 cos squared alpha equals cos alpha plus 1. Now this time there's no need for the substitution because actually it's already got the cos squared alpha, the cos alpha and the constant term. But the key point here is we're working in radians. So this might be something that would arise from a substitution, or in this case we might be just given the equation to solve. So we rearrange it into the quadratic form, squared term and linear term and constant term. We factorise this expression, which will be 2 cos alpha plus 1, cos alpha minus 1 equals 0. We write down the two equations that need to be solved. Cos alpha equals minus a half and cos alpha equals 1. And then we solve these. We'll turn our attention to the more difficult one. First of all, cos of alpha equals minus a half. We're looking for answers in the second and third quadrant. The inverse cosine of a half is an exact value. So this could quite easily be a non-calculator question. You need to look at your exact value triangle, where we have 60 degrees, or pi over 3, and we have 30 degrees, which is pi over 6. So the inverse cosine of a half is actually 60 degrees. Cos of 60 would be 1/2. Now we need 180 minus 60, which would be pi minus 60, or pi minus pi over 3, which is 2 pi over 3, and we need pi plus pi over 3, which is 4 pi over 3. Cos alpha equals 1 on this side only occurs when alpha equals 0 or 2 pi. So there are our answers that we have obtained from the equations, but finally we need to think about the range of solutions. All that is required are solutions between 0 and pi, meaning that this solution is not acceptable and that 2 pi is not acceptable, and we just score these out and finalise our answers to be 0 and 2 pi over 3. Study that example carefully. It might be an idea to pause the video. Finally, example 6. Find the solutions of the equation sine squared p minus sine p plus 1 equals cos squared p, for p is between pi over 2 and pi, 90 degrees and 180. This is an unusual question, but it's useful to help explore some of the ideas. Solutions suggesting that there may be one or there may be more than one. We have a strange equation here because we don't seem to have cos 2p or sine 2p. What I do notice is that we have sine squared p and cos squared p. If they were adding to each other, we would have just one, but we can see that they will not be added in this equation. Actually, we have to subtract one from the other. So by bringing this sine squared p to the other side, or taking it away from both sides, we have minus sine p plus 1 equals cos squared p minus sine squared p. So this is a sneaky question because we have to realize that that is actually the expansion of cos 2p. So I can replace that with cos 2p if we like, and then resubstitute cos 2p for one of the better choices. So in fact, this is just the same as this, but this is also just the same as 1 minus 2 sine squared p. Here I'm using the third choice of the expansion. Now we have all sine terms, all single angle, sine p and just sine p squared. So this is a quadratic that can be rearranged, and luckily the 1 cancels, so we have a simple factorization and then 2 equations to solve. Now solving sine p equals 0 is just 0, 180 and 2 pi. But we only want answers between 90 and 180, so none of those are useful. And solving sine p is a half. Well, the inverse sine of a half is 30 degrees, or pi over 6. And we know, of course, that the answers are in the first quadrant and the second quadrant, so it will be 30 and 150, or pi over 6, and 150 is 5 pi over 6. As it turns out, only that one fits the criteria, so that is my final answer. I hope this video is helpful. I hope that you are able to solve these equations with some degree of confidence, and I assure you that with practice you will definitely improve.